The latest and greatest episode of CS 340 with your host Frank and co-host Payman is another easy, casual conversation, mostly about outlier detection today. So it was probably going to be a little bit short anyway, so no worries in terms of that, except that I lost your attention. Cool. I should say that there's a big conference deadline coming up. I clear on Friday, so I've been working like a dog and up late and up early both, so I'm a little tired. And we're in my probably least favorite two lectures of CS 340 because the material is a little waffly and yeah, that's just what it is. So it's important stuff. It's still really interesting. You can make complete careers out of working on the problems we're going to talk about today and on Friday. But for me personally, it's not my favorite. I like to be pretty methodologically intense, and what we're going to talk about today anyway is pretty straightforward. Last time we talked about hierarchical clustering. We in particular talked about agglomerative or bottom-up clustering, and pointed out that hierarchical clustering gives you much more structure, or reveals much more structure about the data, because man, the configuration is just all over the place today. It produces clusterings at multiple levels of granularity simultaneously, basically, right? The output is what is called a dendrogram sometimes, or a tree diagram, right? And we remember how we did this. We clustered, and then we found what's next closest, and so on and so forth. And this builds a hierarchical representation of the data, reveals a lot of structure. You can usually think of a hierarchical clustering algorithm as non-parametric, because at the finest level, particularly when you're doing agglomerative bottom-up clustering, each individual data item is in its own cluster. So basically, the dendrogram or cluster represents the entire tree. Right? And we talked about the hierarchical clustering has as its roots all the data, so it will grow in complexity with the size of the data, and therefore is non-parametric under our definition. We discussed some application areas, classifying animals, hierarchically clustering animals, clustering languages, so on and so forth. It's worth mentioning because it appears a lot in the literature, and sometimes it can be a little bit confusing, but once you know what's going on with hierarchical clustering, it's not such a big deal. Biclustering is basically the idea of clustering both the examples and the features somehow simultaneously, right? And it gives you feature relationship information. And there's a really simple and very popular method, which basically says run a clustering method on the examples, right? So just take your data matrix X as usual and cluster the rows, right? Then transpose the matrix and treat the features as rows and run your clustering algorithm again, right? And what you get is some sort of thing that allows you to look at your data matrix and discover patterns that are joint over both the features and the examples. So if this is our standard data matrix X, having clustered it in a flat way in the example space says that these examples are clustered together for whatever reason. And then if we cluster in feature space, it says these are clusters. There's 3 clusters of examples and 3 clusters of features. And just by looking at the X data matrix plotted as a heat map / histogram, regardless of the application, we're not thinking about a particular application here, right? You can see that the reason why this particular set of examples is clustered together has something to do with the relative feature values in the various clusters of features, right? So it basically can help you see why things are clustered. And there's application-specific interpretations for basically all of this, right? And a common visualization that you'll see of biclustering algorithms when, in particular, instead of using flat clusters like we did here, where we just said, for instance, here's k-means and we're going to run it in this feature and example space. You can also do hierarchical clustering or hierarchical biclustering. What you'll look at is, again, this is just a permutation of the rows and columns of the feature matrix X, right? Where the permutation of the rows is done according to the hierarchical clustering, right? So the split between these different sections of the data corresponds to splits in the tree. So these are split at this level of the tree. These are split at this level of the tree. These are split at this level of the tree, so on and so forth, right? So we get progressive refinements of our features, the clusterings of our features and our examples. And these kinds of visualizations where you have the dendrogram, i.e. the hierarchical clustering tree, the heat map, which is just the feature matrix, and the biclustering of when you cluster both the features and the examples, is very popular in biology and medicine. And basically you can go in and you can say, okay, maybe these are particular, genes here and cells that we've looked at here, and we can say, okay, well, there's actually something going on interesting here. There's something going on interesting here. There's something going on interesting here. And you can go do science trying to say, okay, these cells are sort of behaving in the same way, but oh, look, actually these cells are behaving in a particular way. This cluster of cells is behaving in a particular way. And oh, look, their activations are also clustered in some sort of a meaningful and interpretable way. Right? Okay. Maybe more importantly for us as machine learning people is to recognize that there are other clustering methods that you can actually employ. In particular, there are probabilistic clustering methods that you'll see in 440 and 540. One of the ways that you can write down a probabilistic clustering method is that you can say, there's some label yi. This is what we've been using that we don't know, that comes from some distribution over the labels, and then each data item conditioned on it being part of some cluster comes from some distribution indexed by the cluster. This is very statistical notation, but it says basically if this is a class-specific normal distribution here in 2D, for instance, right? And if you happen to know the cluster assignment of every individual data point, 1, 2, 3, such that we knew their association, then the probabilistic clustering algorithm becomes one of sort of maximum likelihood and some sort of probabilistic model, which we'll talk about later on in the course, so you don't have to worry about it too much right now. The point is that you would be able to take generic expressions like this, turn them into some sort of objective function, have a coherent probabilistic interpretation of what's going on, minimize some probabilistic loss function. And in fact, the algorithms that you would derive for something like a Gaussian mixture model with hard assignments and unit norm assumptions would end up being, for instance, k-means. So there's a close relationship between the algorithms that we've seen and probabilistic models underpinning those algorithms. There's mean shift clustering, where you find local modes and density of points, and this is an alternative approach to vector quantization. My favorite is basically Bayesian clustering, where again, if you impose a probabilistic model like this, then you can also ask what basically the posterior distribution of all the cluster labels are given the data, which is basically a clustering algorithm under some model. And when you do that, you basically automatically build a weighted ensemble of clusterings, and you can average over those models or clusterings weighted by a probability. So you can inject ideas about how the data should be clustered based on what you know about the world. It's pretty interesting. You can also harken back to the initial part of the course where we talked about feature representations of, for instance, nodes in graphs, where we said, okay, well, actually we can take a node and look at its adjacency to other nodes in a graph and basically build an adjacency matrix and have that be a feature representation of a graph. We can do clustering in feature spaces like this using spectral clustering methods or graph-based clustering methods in general. And we can cluster data described by graphs. So if you have a friend graph, right, you've got high school friends and university friends and partner friends, and you can sort of find these clusters of friends based on basically their adjacency and other kinds of features from the graph. Or in Wikipedia, you can look at the links between them and the adjacency between them and find clusters of articles about musicians or superheroes or athletes or something like that. And again, these graph-based clustering algorithms don't necessarily have to only rely upon the adjacency matrix, but there could also be other feature vectors related to the content of or related to the vertices themselves, right? Cool. So we can do, graph-based clustering straight away by just using one of our clustering algorithms and building a feature representation of the vertices in the graph in terms of either their adjacencies or the actual content associated to the vertex. Questions at this point? And I hope the audio quality is okay. I have to be on Wi-Fi right now because in addition to everything, my wired routing device totally blew up as well. Audio is okay?
Yeah, it's pretty good.
Great. Okay. No questions. Okay. So I, in the standard tagline in the last lecture, basically talked about like how to really miss or find a hole in the ozone layer. There's a problem, especially for people who don't tan well on top of their head, which is that there's there was a large ozone hole, a missing patch of ozone in the upper atmosphere, and it was discovered in 1985. Turns out that this data had been in the satellite data since 1976, but it was flagged and filtered out by a quality control algorithm that basically treated it as some sort of outlier. So cool. I see that there's a question that managed to miss the pause section of the course. So thanks, Payman, for keeping me on top of it. How do we assess clustering algorithms in terms of accuracy, or is it even possible to assess accuracy of clustering? It's amazing, actually. Just as a little side comment for Akeem and others, that the like disease in the English language extends even to writing, and my 6-year-old son has started using it as well. The like there is somewhat unnecessary. Or is it even possible to assess accuracy of clustering? So I think we even had examples of I think we even had slides where we said it's very difficult to establish a notion of what a best clustering is, right? I think it's one that is useful. That I think is really at the end of the day, how you decide whether or not it's a good clustering. You could you can have labeled examples that should be clustered together, and you can assess whether or not those examples are clustered together. And that's one way you can do it. Obviously, for an algorithm like k-means, there are objective functions, so we can actually look at the objective function value and say whether or not within a particular hyperparameter setting you've done a good job of clustering according to the metric, and that's basically it. Anaf, yeah. So does that kind of warrant domain experts looking into the results to assess how good they are? It's often actually what happens with clustering, right? So one metric that you can use is indeed, do the clusters that are discovered correspond to human notions of what those clusters should be in this kind of data? Yeah, unfortunately, yeah. I was a little bit late to lecturing in addition. because we were designing the midterm examination, and there'll be an opportunity for you to experience whether or not a particular clustering is useful or not in the midterm examination. So you'll have an opportunity to explore this yourself soon. Cool. Awesome. So outlier detection, that's basically the, Shauna, are we going to have to code during the midterm? Yes, you're going to have to code a lot. And you're gonna have to do new stuff, even derive stuff. It's gonna be great. It's gonna be super fun. You're gonna love it. I like making exams learning experiences. That's gonna happen here. Anyway, so outlier detection, that's what we're talking about. What's outlier detection? It's finding observations that are unusually different from the others in some sort of a way, right? It's also known as anomaly detection, so on and so forth. You might want to remove the outliers, or you might be interested in the outliers themselves. So, like one of the best questions I've ever gotten in the class came in the last section, and I'll relate it here, which is like, why remove outliers? What's the point, right? And this is a pretty good example. We haven't talked about regression. We're going to get there pretty soon. I think starting next week we'll start talking about regression. But the main point of wanting to maybe remove outliers is that if you were to fit some sort of regression model to this data, right, it's very likely that if you have an outlier like this in it, your regression model will have to accommodate that in some sort of a way when you fit it, right? And that means that either on a validation set that you've withheld, or on actual test data where you'd like to make a prediction, your prediction is going to be way, way off. So basically your model is going to suck because you have fit it on data that has some sort of bad characteristic, right? Has spurious values in it, right? So finding outliers and removing them, even actually posing whether or not certain data items are outliers as a hyperparameter fitting problem, is a good way to think about why we're kind of talking about outliers now and why they matter, right? You might want to remove them, or you might be interested in them themselves. Like you actually might want to say, oh, I want that one because it's somehow different, and this is a trading opportunity, or this is a denial of service attack, or something like that, right? Cool. There are lots of sources of errors. It's pretty obvious. You can actually make measurement errors. You can have data entry errors. You can have contamination from cosmic ray, cosmic rays hitting your storage device or whatever, right? Rare events that are not well explained by the model. There are lots of applications of outlier detection. Data cleaning is a big one. Security and fraud detection, like detecting network intrusions from logging data, or denial of service attacks from the same. Fraudulent credit card transactions. Is it common for me to spend this much in being around the world? I don't know. Detecting natural disasters, underworld, or finding new classes of things, right, that are not explained by your model well, so on and so forth. And there are lots of methods. We're going to talk about all the methods for all of these methods for outlier detection. They're sort of semi-obvious, right? One is model-based, the next one is graphical approaches, another one is clustering-based methods, another one is distance-based methods, and in fact, we can use our supervised learning tools to do outlier detection as it is. And this is one of the reasons why this is not my favorite part of the lecture series, is that even though we have to talk about it, it's even more ambiguous than clustering, right? Like, what is an outlier? It's very much in the eye of the beholder, right? So what's nice is that basically all the stuff that we've talked about so far in the course can be used in service of doing outlier detection. But the first thing that you should do is basically do some sort of sanity checking, like basically manual type checking, to make sure that, like the quantity of eggs that's consumed at a particular time is not totally insane, that, you have mistyped entries or out of range entries, like you can't like generate shellfish while you're eating unless you can, run time backwards, so on and so forth, right? So would any of the values in a particular column cause some sort of a type error relative to the rest? Are values out of range for numerical features? Are there, unique entries? What are the valid unique entries? Like is to a valid label for the sick column if it's just sick or not sick? Probably not, right? Are parts of the table duplicated? The issue is that these kinds of errors in real data are very, very common, right? And we talked about this and we said we're not going to talk about it much in the class. Today's one of the days we talk about it, right? So the first thing we can do is do some sort of model-based outlier detection where you fit some sort of probabilistic model. We haven't really talked about maximum likelihood. You might find out a little bit about it on your midterm and then we'll learn about it afterwards, which would be kind of fun. So outliers are basically under some probabilistic model examples that have low probability under that probabilistic model. So one example one way you can go about doing this is that, say for instance, is if you have a single feature here like so, you can assume that the data follows a normal distribution, right? That's maybe reasonable for this data. Here's some, empirical histogram, right? We fit a normal distribution to this with some mean and some, sorry for the color, standard deviation, right? And then we so-called z-score the data, which is to say, if we're going to do outlier detection, we want to be able to do this in a unitless space. So if we subtract off our estimated mean divided by the standard deviation, where our maximum likelihood estimate for the mean and our maximum likelihood estimate for the standard deviation looks like this, then the z-score, or z-score, is for a particular data item, or in this particular case, a one-dimensional feature, is what's the number of standard deviations away from the mean is this particular value, right? And it can be positive or negative, right? You can have a z-score that's relative to the unit norm 0 basis because we subtracted off the mean, right? So we can actually just say if an outlier for any particular, we can do outlier detection by just saying that if the absolute value of the z-score is greater than some threshold, then we say that that's an outlier, okay? That's one way to do outlier detection. It basically corresponds to setting some sort of limit on this and saying,
Yeah. Would it make more sense to use a t-distribution given the true threshold when the standard deviation is unknown?
So, okay, this is a lovely question, Alan. So the real root of your question is the distributional assumption you make about the data correct or not, right? And this is a hyperparameter that you have to consider, right? If your data looks like this, is this t-distributed or is it Gaussian distributed? And under a t-distribution, which has heavy tails, the probability that this has low probability below some threshold is much lower than it would be under a Gaussian distribution. So in fact, your suggestion of a t-distribution here, which is of course well, I won't go into it, it's the marginalization of a normal with a particular prior over the standard deviation. It's an infinite mixture actually. That choice actually is one that is robust to outliers, generally speaking. So if you use a t-distribution, you're saying, actually, I'm going to give high probability to even tail events. So you're basically saying when you say t-distribution, something needs to be really, really far away from the mean in order for it to be treated as an outlier, because the probability trails off relatively slowly. But if your data is actually t-distributed for whatever reason, then that's probably a better thing to use as a model of your feature anyway. And just to point out, like what we're talking about here right now as an example is just fitting a probabilistic model to a single dimension, right? When we're doing outlier detection, more sophisticated approaches are to build a probabilistic model for all dimensions simultaneously, and then ask about some sort of probability cutoff in that very high dimensional space, right? Turns out it's a very hard problem, and it's basically a density estimation problem, and that's hard. Because just like with the z-score, yeah, go ahead.
Yeah, I was just, you go ahead, I will ask it later.
No, please, go on.
I was just wondering, is there a difference between noise and outlier?
So if we go back to, I don't know, I could have just drawn it, I guess. If we go back to here, right? I think that it's a good question. I think it's a good question. I'm sure lots of people are thinking about it. If the true relationship between X and Y here is, actually this, quadratic surface, right? Then you can see that there's noise about this, right? There's measurement noise, right? But I would say that an outlier is different because it has low probability under a reasonable modeling assumption about the noise distribution, right? So indeed, an outlier is in the eye of the beholder, and what is an outlier depends on your distributional assumption about the measurement noise, basically, right?
Yeah.
So what's the difference? Magnitude. It's basically, where do you set this value, this threshold?
Okay. So basically, when you want to add like noise to your data set, sometimes you basically add like some outliers, but considering like that magnitude, right?
So this is a good question, and I'm very glad that we're having this conversation. When you add noise to the data set, you're usually adding noise not to the labels, but to the inputs.
Yeah.
Right. So that's very different, right? So here we're really thinking about there's some outlier in the label space, or there's some outlier in a general sense of the joint distribution of input and label. And generally speaking, you are very, very careful to only add a certain amount of noise so that the relationship doesn't change.
Sure.
Right. So that's quite different, right? So there are some obvious problems with the Z-score, and it comes down to basically distributional mismatch or whatever between your assumed distribution and what the distribution of features are. For instance, when you estimate the mean and variance, those estimators are sensitive to outliers. So there's things that we can do. We talked about summary statistics before, like quantiles, or it's sort of obvious. You can just sequentially remove the worst outlier until the halting procedure, until you decide to halt or whatever, right? Basically, the Z-score makes a normality assumption about your feature, which means that it makes a unimodal assumption, right? The data is concentrated about the mean. So if you fit a normal distribution to this empirical distribution here, what's an outlier? What's the low probability? This is a bad model for this data, right? So, and we're just having a pleasant conversation about this at this point, right? So is the red point an outlier? I would say so, right? But what if we add the blue points? If we're using the Z-score, then this is not an outlier, right? In fact, it's actually, it has the lowest Z-score if we actually fit some bivariate normal distribution to this data, right? That would have the lowest Z-score, right? So, in the second case, it's, in the first case, it's a global outlier, because if you fit a bivariate normal distribution, it's going to have very low probability under that, right? The first case is a global outlier. The second case is a local outlier. It's within the normal data range, but far from other points. So it's kind of difficult to decide exactly or define exactly what is an outlier, right? So, so can we have outlier groups? Maybe. Is that a group? What if we add these? Is that an outlier? Are those all outliers? Probably not. Tough to say. So how do we go detect these things besides Z-scoring and thresholds? We can just look at the data, like we can plot the data and have a human decide if a particular data point is an outlier. So we can do box plots, right, which we already know about for the visualization of quantiles and outliers, right? You can only look at one variable at a time, but you can identify outliers relatively straightforwardly, just graphically, right? Same thing with scatter plots. We've already seen this example, but there's our data set, and this thing clearly is not part of the natural data generating process, right? Of course, you're going to look at two variables at a time. We can still do, scatter plot arrays where we look at, all pairs of variables, and, maybe you go in and you're like, oh, is that an outlier? Or are these outliers? And you have to go and look at all the different perspectives and identify that data in all the different perspectives, and it's you know, complicated. Okay, and it's still only 2 variables at a time. We'll talk about principal component analysis later, but one of the things that we'll talk about when we do unsupervised or parts-based modeling or whatever unsupervised learning of parts-based models is we'll learn how to project data into a lower dimensional subspace that preserves, in some sense, the most information about the high dimensional data set that we can, right? So if we do this projection, project data on the first 2 principal components here, then it'll see high dimensional structure. But again, there's underlying PCA, and by virtue of that model being fitting PCA means that it's sensitive to outliers as well. So this chicken and egg problem that we saw with, you know, computing z-scores after doing maximum likelihood estimation still applies, right? So maybe there's other ways that we can do outlier detection, and indeed there are. So we can use clustering methods to do outlier detection. You can cluster the data and then find points that don't belong to clusters or are far away in some sense, right? So we can use k-means. This is our k-means example, right? We have a data point over here and it's far away from the exemplar for all of these clusters. You know, it's an outlier. Or you can find small subclusters. Maybe there's a cluster of data points way over here that's separated by some other hyperplane, right? You know, maybe we just say very small clusters, they're outliers, right? But we could do density-based clustering like DB scan, right? We already know that in DB scan, outliers are points that are just not assigned to a cluster. So we've got some sort of density thing. And of course, we've got, you know, outlier groups, we've got local outliers, and it solves some of the problems that we were talking about, right? When I talked about hierarchical clustering, I showed that basically, you know, or indicated that often to debug hierarchical clustering to make sure that the hierarchical clustering algorithm is producing some sort of reasonable result, you actually intentionally put outliers in and make sure that they're amongst the last to join the hierarchical clustering, right? So one way to look for outliers is to do hierarchical clustering and look at the stuff that joins the hierarchy last or latest. This is a good way to find outlier groups, right? Like basically everything we're doing, you know, outlier detection approaches are basically based on distances, some sort of norms between, you know, feature vectors and so on and so forth. So can we skip the model or the plot or the clustering and just measure distances? For instance, like how many points lie in a radius epsilon, or what's let's do some sort of like rank statistic, right? What's the distance to the kth nearest neighbor, and set some sort of threshold. So Raymond Ng in the computer science department still here, like was one of the first people to write a paper on this subject, and you know, the general idea kind of goes like this, right? So let's do k nearest neighbor outlier detection kind of thing, and for each data point we can compute the average distance to its k nearest neighbors, right? And from this we can choose points that have the biggest values of the average distance to its neighbors as outliers, right? So they're points that are far from their k nearest neighbors. So again, right here we have some data set, and you know, if we compute the 5 nearest neighbors for this point, they're all pretty close. Right, so the average k nearest neighbors distance for that point is very small. The 5 nearest neighbors for this point, who knows what they are, but the average k nearest neighbors distance for that point is going to be pretty large. So if you set a threshold, you can say, okay, at this threshold value, everything that's outside of this, that's above this threshold is an outlier, right? And like the random forest experiment, there was a survey paper in 2016 that compared a bunch of different methods on a bunch of different data sets and found that k nearest neighbors based approaches are best for finding global outliers. Local outliers were best found using local distance-based methods that look like this, right? The problem with this k nearest neighbors approach is that we have a problem with differing densities, right? So this outlier O2 has a similar density, right? In other words, a similar distribution of nearest neighbor, k nearest neighbors distances as, for instance, one of these points. right? It's you know 1, 2, 3, 4, 5 nearest neighbors basically have all the same length scale as this. So as soon as you try to cut off this one, right, you basically cut out all of these, right? So that's a little bit of a problem. So the basic idea behind local distance space methods is this, right? This outlier O2, this one right here, is relatively far compared to its neighbors. Like it's relatively far to its neighbors compared to the average distance of its neighbors to their neighbors, right? It's just kind of wordy, but it's complicated. It's straightforward, right? So we can compute something called an outlierness ratio of an example, which is one, you know, like first we just compute the average distance of data item I to its, for instance, 5k nearest neighbors, and we normalize by the average distance of I's neighbors to their k nearest neighbors, right? So if outlierness is greater than 1, then a data item xi is further away from its neighbors than expected. It's differently distanced to its neighbors than its neighbors itself, right? So if we compute this outlierness ratio for this data set, which I'll zoom in on because I can, right? These are the thresholds, or these are the outlierness ratios here, right? And now we can, you know, Payman and I are you and whatever, right? We can go off and decide what our threshold is. So I would say my threshold for the outlierness ratio is 2, and everything that has an outlierness ratio above that, you know, this guy, this guy, this guy, this gal, this guy, this gal, this guy, whatever, they are all outliers, and everything else is hunky-dory, right? Cool. Okay, because that's not all the way zoomed. There we go. We can also do something cool like isolation forests, right? So now we have some vocabulary that we can use between us. So we can do tree growing where each stump uses a random feature. Like there's no like find best stump. You just take a random feature and take a random split. Okay, cool. You grow the tree all the way until every leaf has one example, when each example is isolated, right? The isolation score is the depth before an example gets isolated. Okay, so you know, if you look at xi here and you just used random features, you know, a random feature and random splits, it's going to take a relatively long time to actually split xi away from its neighbors in expectation, right? So for x naught, it's not going to take that many splits to actually isolate x naught, right? So the idea is that outliers should be isolated quickly, and inliers would need lots of rules to isolate, right? So in this particular case, you know, you needed 12 splits in order to isolate this. So it's probably an inlier, and over here you needed just 4 splits, so it's likely to be an outlier. And the isolation forest idea is that you basically do this for lots of different random trees, and you take an average isolation score. Now you have something else that you can threshold to decide whether or not something is an outlier. Okay.
Is it pretty costly?
Well, I mean, it's going to have the same, basically the same. Well, it has the same complexity of random forest without actually having to compute the inner find best stump loop, right? So it's actually not that bad. You're just making random trees, right? Yeah, it shouldn't be that. It shouldn't be that bad. We can think about it if we want to, but. So why wasn't the ozone hole layer discovered for 9 years? Well, it's hard to decide whether to report an outlier. Basically, if you report too many of them, you know, users will turn you off. It's the boy who cried wolf problem, right? This is why, you know, you should look up the base rate policy thing if you don't know about it. But it's one of the reasons why most antivirus programs don't use machine learning methods. So we can also actually use our supervised learning techniques to do outlier detection, provided that somebody goes off and labels what those items, what outliers are, right? If you give me a bunch of credit card transactions and you say, this one's fraudulent, this one's fraudulent, this one's fraudulent, right? Then you can use supervised learning to actually try to decide which transactions are fraudulent or not based on their, you know, features. So you just label a bunch of stuff, and then we can use whatever supervised learning techniques we have at our disposal, right? We can find very complicated outlier patterns, right? So classically, credit card companies would use decision trees to do this, right? But doing this requires actually providing supervision. You need to know what outliers look like, right? And obviously, when you do supervised detection, you're not going to detect new types of outliers. Okay, like I said, even though there was technical fiasco, we have a pretty light lecture today, and we've actually made it somewhere again. Anif, what's the opinion on hybrid models, unsupervised to get labels and supervised as discussed? Do you understand that, Payman?
Supervised to get labels and supervised and stuff. Not sure.
I think, Alan, I think I agree. I think we said, like, we cluster the data, we get some labels. Yeah, that's fine. Yeah, and then what? And then supervise as discussed. Then train it with a supervised model for outlier detection or for just general purpose machine learning for outlier detection. Yeah, but basically what you're saying here is what you're presaging, prefacing, whatever, is that unsupervised methods you can indeed view them as ways of generating features for supervised learning techniques. What you're saying is, we need outlier detection, we need labeled data, we need features in order to feed into that. We can either use the raw features or we can use unsupervised learning techniques to generate other features as well. You could think of this as a kind of a stacking. It's not quite the same because you don't have labeled data for the unsupervised feature extraction module system, whatever. But indeed, actually, dimensionality reduction or unsupervised feature extraction can be extremely powerful for all kinds of applications, particularly supervised learning, and outlier detection with labeled data is just one example of supervised learning. So yes, indeed, I think that we will talk about this at length in the class if that's what if that's what we're talking about here. So we've made it to the end of part 2. We've got some key concepts, right? So we focused on 3 unsupervised learning tasks, right? We talked about clustering, where we did partition-based, where we chopped up space like k-means versus density-based db-scan. We had flat clusters versus hierarchical clustering in the form of agglomerative clustering. We talked about vector quantization as a loss decompression kind of thing that basically uses k-means clustering or corresponds to k-means clustering. And we talked about the label switching problem, which is something that needs to be introduced because it's an important problem that you need to know about. We talked about outlier detection. We did that today, right? We surveyed some common approaches and said the problem is not well defined. So today's summary, we talked about biclustering, where we clustered the examples and the features. It's quite common in the physical sciences. And we talked about outlier detection, right? So we talked about a bunch of ways to do that: model-based, graphical, cluster-based, distance-based, and supervised learning for outlier detection. So I think this is not true. I think we do recommender systems next time and some other stuff. We'll see. I'm not 100% certain, but hopefully we'll start supervised learning with continuous labels very soon. Cool. Questions? Thank you all for sticking around. I appreciate it. And if Akeem is still here, I apologize if indeed you took that as some sort of a comment on your English skills. It was not. Current information, Michael, is that you're both supposed to submit. We will post something on Piazza.
Also regarding the grade scope ID, we're going to post something in Piazza to fix the
Yeah, we need to do that. I should have mentioned that in this class as well, but I had it in my head to just mention it on Friday to everyone. Cool. Thank you, Raymond. I really like the question you asked today. It was good. It's like it adds value. It's wonderful. All right, if there are no more questions, I'm gonna sign us all off. Thank you very much.